Okay, let's verify this identity. As we look at it, remember the goal or the purpose of verifying is to make the left side look like the right side. We're trying to prove that these two sides are equal. And if we notice, we have two things being multiplied together here. And so let's multiply them. So let's go ahead and multiply. Also, I want you to notice that we have the exact same terms in here, only one is separated by a minus and one is separated by a plus. This is going to create the difference of two squares, and if y'all notice that, it will help because it makes multiplying them very quick and easy. So we can take and just square the first term. So we end up with secant squared of u, and then it's always difference of two squares, and then we can square the second term. So we end up with tangent squared of u equals 1. Now, there's lots of different ways that we can proceed from here. I see some Pythagorean identity possibilities. So let's go look at our Pythagorean identities for a minute, and here they are. We have secant squared right here, and we can replace that with tangent squared of theta plus 1. So let's try that, because then we'll have everything in terms of tangent. So I'm going to replace this guy right here with what it is equal to, which is tangent squared. I'm going to use the variable u, and then it's plus 1, and then minus tangent squared of u equals, we can go ahead and write 1. It's easy to write. These parentheses really don't mean anything. I just wrote them because I replaced secant squared with what it's equal to. So we don't really have to do anything with those parentheses. And we notice we have tangent squared of u plus 1 minus tangent squared of u. So those tangent squareds, when we combine those, combine like terms, they cancel each other out. So we end up with just 1 equals 1. Done. Okay, here's another identity we can verify. Remember, we're trying to make the left side look like the right side. We only want to work with one side of the equal sign. All right, let's look at this. Our goal is secant squared of x. Well, we have a secant squared, but it's all inside this expression, so we can't really remove it. There's nothing we can factor out. What if we put everything in terms of sine and cosine and see if we can't see what happens? So right here, the 1 is going to come down. Secant squared of x, if I want to change it in terms of sine and cosine, I would have it as 1 over cosine. So I can replace this guy right here with 1 over cosine squared of x. And this is already in terms of sine and cosine, so I'm just going to leave it. Remember, it's on the top. If you want to put it over 1, it might help you. Let's multiply these guys together. So we end up with sine squared of x over cosine squared of x, and we equal 1, or bring the 1 down, excuse me. Now, I'm hoping that you're starting to notice that sine over cosine is the same thing as tangent. Now, I know on your identity chart it is not squared, but as long as all of these are squared, it still works. So right here, I could replace this with tangent squared. So I bring down my 1, and I have 1 plus tangent squared of x. Here it is again, the Pythagorean identities. They happen all the time when verifying. So we have 1 plus tangent squared, and notice here we have tangent squared of theta plus 1. Well, what does that equal? Secant squared of theta. It doesn't matter the order when we add things together, so I can swap this out with what it equals, secant squared of theta here, or secant squared of x here. Now notice, there's our goal. Secant squared of x, and we're done.